Okay. So just the plan for today is, so we got formulas last time, and the plan for today is to finish implementing them, test them, and then use them. So the formulas are these GDO formulas, so this category GDO. And it all looks abstract, but it actually works, so you'll see. And then on Monday, so the proof I gave to these formulas was like half intuitive, half precise. So I will give a second proof on Monday, and it will be completely analytical. So when I say analytical, I mean not like analysis, I mean completely algebraic. But no fancy combinatorics, just calculations. Okay? So that's the plan. Now, but let me remind you what the formulas were. So I have this category in which the elements are Gaussians. So scalars times the exponentials of quadratics. And I want to tell you how to compose one Gaussian with another and get the result a third Gaussian. So since half my variables are Greek, or so some of my variables are Greek and some of my variables are Latin, I will decompose my quadratics into three pieces. So E is the Greek-Latin piece, F is the Greek-Greek piece, and G is the Latin-Latin piece. And then I view each Gaussian as a coupon that has on it several pieces of information. So omega, E, F, and G. And I remember that F is a quadratic with Greek-Greek because it's pointing in the Greek side. Latin is a quadratic with G is a quadratic with Latin because it's pointing at the G side. Similarly, E goes across. So I have two such coupons. I want to tell you how to compose them. So I want to find what are omega, E, F, and G of the composition. So first of all, the composition makes sense, like in a category, only if the variables here match the variables here. And what I really mean by that is that the variables here are the duals of the variable here. So the composition makes sense only assuming A2 is B1 dual, the dual. So I mean, each A is the dual of the corresponding B. And if that is the case, then you have some like argument which has to do with walking on those pictures. And in fact, it's very reminiscent to Feynman diagrams in physics. So if people familiar with Feynman diagrams would know that this is exactly the same kind of calculations that occur with Feynman diagrams. But we'll see that later. And anyway, here are the formulas. So the E of the output is, well, E1, then an arbitrary number of FG loops, then E2. Arbitrary number of FG loops is the sum of a geometric series, so you get identity minus F2G1 inverse. Likewise, F is given here, G is given here, the new omega is given here. For the moment this is given, now I want to implement it and see if it works. Okay? So, yeah, let's start with the implementation. So, actually we started already, so this is a notebook that will be available, of course. And first thing, I go to the right directory and I load all the common programs. Just to be clear, the common programs are basically, you load basically a list of Ribonauts, the thin position program, the PD of GST48, the programs that converts a node to an RVK, and in fact I've just added to it. So common, I will always add to it. So this is the program that gives, so Z is the program that given a node, an RVK of a node, so a rotational virtual node, and assuming that an operation M, and so the multiplication operation, and eta, and R, and C, so assuming all of these things are are already defined, Z just computes the corresponding invariant. And then ZF is the same, but first you bring node to thin position. So these are programs from before, so I'm just loading them, and here is the new stuff. So first of all, a hack to fix series data, that's not interesting. I went through it last time, but it's just not interesting. Then I'm defining the duality of between the variables. You know, so P star is defined to be, right, P star is defined to be pi, the dual of X is defined to be psi, and so on. So for example, if I do P and then star, I'll get pi. But also, if you have any variable named U, subscript I, its star is defined to be the star of U sub I. So therefore, if I will type P sub 7, and then star it, I get pi sub 7. And finally, if you want to star a whole list of variables, you just star each one. So, you know, if I'll do P psi 6, and I'll star all of this will be pi and x6. So that's just, okay. Then, okay, so, well, my plan is to test this composition law. But of course, this is supposed to be a subcategory of the category of generating functions. So I first have to implement the category of generating functions if I want to test it. So my notation for the category of generating function is that if you have a morphism from a set A to a set B, I will call it blackboard G for generating, sub A goes to B, and in A I will put a set of Greek letters, and in B I will put a set of Latin letters. And then some function, the actual generating function G inside, or L inside. So now I'm defining, so if you have a generating function which is in which the Greek letters are A1s and the Latins are B1, and a generating function L2 with Greeks A2 and Latin B2, then their composition, assuming B1, the duals of the B's are the A's, is a module in which you do the following things. First of all, you so I have to remind you how to multiply, how to compose generating functions. So if you have L1 and you want to multiply it with L2, sorry, to compose it with L2, one way to do it is to just multiply it and apply the rule that anytime you see a letter, so I mean if L1 goes from A1 to B1 and A2 and L2 goes from A2 to B2, then I take this thing and apply to it the rule that every time I have a letter in B1, so for every B inside B1, every time I see B times B dual raised to some power, so every time I see b to the p, b dual to the q, I map it to delta pq p factorial. So basically, if the Latin letters of here match with the Greek letters of here, come with the same power, then then the pairing is p factorial, and otherwise you get 0. Okay? So here it is. Oh, and I should further say that A1 might have letters that interfere with the letters of A2, have the same names. And B2 might have the same names as the things in B1. So just to avoid these confusions, I first rename all the letters here by putting bars on them. So, oh, and that was a mistake. Maybe I shouldn't have called this B, I should have called it Z. Because B is what I use for the bar. So what I do is, first of all, I take L1 and I replace, for every x in B1, I replace x by bar of x. And I take L2, and for every zeta in A2, I replace zeta by the bar of zeta. And then I iteratively, so I go one after the other on the variables in B1. So for each x in B1, I replace R by R. I replace R by R, to which I apply the rule that if you have bar of x to the power p, and then bar of x dual to the power p, I replace it by p factorial, and then if there is any remaining x or x dual, it goes to 0. That's the same as this delta function here. And then I output a generating function whose name is R, and with which goes from A1 to B2. So I mean, it's basically, well, I don't know what to say. This is it. And that's not interesting, and we did it last time. Anyway, we tested it last time. It works. I have nothing to say. Okay, now on the screen is exactly what's on the board, so I have nothing to say about it, including a picture of Feynman. But now I have to start implementing it, and then testing it, and then using it, okay? So first of all, I need a name for such a thing. So my name for such a thing would be Blackboard E of omega and Q. Sorry, Blackboard E. You know what? Maybe I was too ambitious writing so high up. I should restart it here. So my name will be, the name for this coupon will be E sub A1 goes to A2 of omega 1, comma Q1. Sorry, A1 goes to B1. Okay? So I'm just starting to build infrastructure for morphisms like that. So if you have an E element with subscript S1, so I mean S1 here stands for both the domain and the range. And I want to compare it with another one with subscript S2, and the payload is omega Q1 here and omega Q2. All I have to do is to, so I'm checking, this is how to test when two things are equal. So they're equal if S1 is equal to S2, and this one is equal to that one, but only after you simplify. So I want mathematically to simplify, to test, basically to test, if it's the same thing algebraically and not just as a combinatorial expression. If the formulas actually agree. Anyway, Then, I actually didn't say it, but it's a useful fact to know that our category is really well, there are products. There is a technical name, symmetric, monoidal, strict symmetric, monoidal, something. But really, you can multiply morphisms, which amounts to say, which has to do with the fact that you can multiply generating functions. So if you have two generating functions, you multiply them, you get a generating function whose set of variables is the union of the set of variables. And in fact, if you multiply two quadratics, two Gaussians, you again get a Gaussian, because e to the q1 times e to the q2 is e to the q1 plus q2, which is again quadratic. So I'm implementing this. E a1 to b1 with payload omega 1 and p1 multiplied by the same thing with 2 is defined to be, you take the union of the Greek variables, the union of the Latin variables, multiply the omegas, and add the quadratics, because the quadratics are in the exponents, so they just get added. I don't know, there's not much to say about it. This is it. It's been defined. The next thing is another thing to know. So, you know what, maybe I'll skip it. Maybe I'll get back to it later. It's not terribly interesting. Here is the interesting bit. So, this is the core. This is where all the action happens. So, suppose you want to compose an E from A1. Basically, suppose you want to compose this coupon with that coupon. I have to tell you what is the output. So, assuming B1 dual is equal to A2, I define it to be, well, lots of local variables, including one silly little variable which I call M, which is which is just defined to be the Mathematica command table. So instead of typing table, I have to type M, which is a bit shorter. And also M stands for matrix. Okay? So I need the identity matrix throughout. So I let AI be the identity matrix of size the length of B1, which is the same as the length of A2, which is the right size. And then E1 should be like this thing. So how can I get it out of the quadratic Q1? I just need to differentiate the quadratic with respect to all the Greek letters and all the Latin letters. And the matrix of partial derivatives is E1. So E1 is the matrix of partial derivatives of I and j relative to I and j of Q1, where I runs in A1 and j runs in B1. Likewise E2. Likewise F. So F is the partial derivatives where I runs in A2 and j runs in A1 and j runs in A1. So both are Greek. And G is similarly with both Latin. So now I mean, all of this was not yet even a program, and this is just setting up the data. And then I output an E-morphism, so a GDO element, a Gaussian, with inputs A1 and outputs B2, just as I should, and with omega part equal to, well, the formula, and with well, basically you recognize all these formulas. So E1, the inverse of identity minus F2G. So basically this from here to here is the thing that's called E here. But then I want to take it to make it into a quadratic form. So I dot product it with the variables in A1 on the left and with the variables on B2 on the right. And likewise for everything else. And I throw in the halves where I should. And then Mathematica doesn't like empty matrices. So I also made exceptions. So if the set of input variables is empty or the set of output variables is empty, then the contribution to this part of the quadratic is 0. And I mean, but this is basically because Mathematica doesn't like matrices whose dimension is 0. So that's a hack. The content is here. Anyway, so let's enter it. And unfortunately, okay, so now I would like to test it. Okay? But, so what do I test it on? So I just chose to test it on random elements. So I wrote yet another program called random E, so a random E element with Greeks A and Latins B, and with parameter R. So the parameter R is what is the range of the random of the random integers that I'm going to use. And then it's a module in which Ri is a local variable, and Ri is just the command that says compute a random integer in the range from -R to R. And then I make E, which is a table of Greek letters with indices in I, in A, arrow, a table of Latin letters with indices in B, and the payload is a random integer for omega, and then a random quadratic form, which just amounts to you sum over all i's in A, j's in A, and take a random integer times the Greek letters, and then the Greek Latin, and then the Latin Latin. And one extra feature is that, so you see, in principle, I should be worried about convergence. So to make everything convergent, the e's have to be, sorry, the e's don't need to be small because the zetas are small. The f's don't need to be small because the zetas are small, but g has to be small. I've just decided to simplify life and multiply everything by h bar. So everything, and h bar is declared to be, I'm going to regard h bar as a small parameter. So I'll just throw in an h bar in front of everything, and then I'll test that as a power series in h bar, things work. Okay? So, so that's the h bars that appear here. Anyway, so let's enter the, oops, what have I done? Enter the program, and then let E1 be a random E element with inputs 1, 2 and outputs 1, 2, 3, 4. So the inputs are Greek 1, 2, the outputs are Latin 1, 2, 3, 4. The omega part, the scalar part, came out to be 4, and the quadratic form is given here. I have nothing to say about it. It's a random quadratic form. Okay? In fact, you know, if I'll execute it again, it will come out different. If I'll execute it again, it will come out again different. And let's do it one last time. Okay? And then similarly, E2 is with inputs 1, 2, 3, 4 and output 1, 2, 3. So basically E1 is composable with E2 because the output of E1 are the same as the inputs of E2. So here's E2. And now let's compose them. And here's the composition. And if you think it is ugly, I have nothing good to say. I mean, you are right, this is ugly. Notice that there are, and this is 1 over square root of the determinant, which appears in the formula there. And this quadratic form that we get at the end is actually, so here is this quadratic form with this random awful coefficients, but it gets divided by some power series. And the reason it gets divided by this power series is because we need to invert this matrix. When you invert a matrix, you get 1 over the determinant. In fact, the determinant, the denominators are exactly the determinant, which is what happens to the scalar part. So if you look at this thing here, it's the same as over there inside the square root. Well, okay. But now I need to test it. So to test it, I need to check that composition in GDO is the same as composition in Gen. So I need to implement the map which convert a container in GDO, so converts an E container into a G container, so that I would be able to compose. And this is E series, the series of, so I really should, this maybe is a lousy name. You know, really I should have called it G. So basically the G element corresponding to an E expression is, well, you look at omega e to the q, but, you know, there is an infinity problem here. I mean, closed formulas here represent infinite formulas here because of the exponential. So I also have a parameter that goes into G, and this is to what degree do I want to do it. So applying the conversion into G to an E element computes omega times e to the q, compute it as a power series in h bar to degree d, and then expands the result and puts it inside the G wrapper with the same subscript. So same domain and range. Okay? So let me execute this. And then, so what's the E series corresponding to E1? So I'll remind you, E1 is this funny quadratic form. The corresponding E series is, to degree 1. Maybe we should do it to degree 2. So the corresponding E series to degree 2 is some G power series, some G element whose entries are power series in the Greek and the Latin variables, but also in h bar, and it's computed in h bar. Here, this is the degree 1 in h bar, and this is the h bar squared, and I could go on, but you know, it's probably too much as it is. So actually, let's, okay. So likewise, here is E2, and here is the series. This is, so now oops, sorry. Here is E2, and now I convert E1 to a series, I convert E2 to a series, and I compose them as series, and this is what you get. And then, on the other hand, I compose them using the GDO composition, and then convert it into series, and this is what you get, and it's the same. Good, we've just proven that to degree 1 in h bar, these formulas are right. Well, degree 1 might not be convincing, so let's do the same to degree 5. Now it takes a little time because these are huge power series, in fact. But hopefully it will tell us that it's true. It did. Good, we're done. Now, philosophically, how should you view it? So, you know, we've only checked something random. But this couldn't have been, it really, to me, sorry, this is my biases, to me, this is more solid proof than anything I could write by hand. Like if I actually wrote a traditional LaTeX proof, I would be less convinced because there's more chance of a mistake than the probability that this actually came out by chance. So to me, this is convincing. Also, at the end of the day, there is nothing extraordinary here. You know, these are ordinary math formulas. They're not, it's not the Riemann hypothesis. It's just algebra. So now that I know the formulas are true, it's really just a technicality to prove them. So in a way, Monday's class will be a waste of time. No, it will not be, because there will be other useful bits in it. But in a sense, proving it absolutely precisely after we have seen an intuitive argument and a verification is somehow being pedantic. It's not, anyway, but this is my ideology. Okay. The next thing is kind of weird. Okay. Well, okay, you know, now that we know that the formulas are true, maybe we can remove them. And talk about our situation. So, you know, I want to be able to write things like the trefoil. So what's the trefoil? It's a crossing from 1 to 4 times a crossing from 5 to 2 times a crossing from 3 to 6 or something like that. And then I want to apply all the multiplication operations. So multiply 1 and 2 into 1, and then multiply 1 and 3 into 1, and so on. Strictly speaking, this is an element of the form E, no Latin letters, and the Greek letters are P1, X1, up to P6, X6. You know, let me short it by just writing 1, 2, 3, 4, 5, 6. Okay? As an element of the category, if I multiply these three morphisms, I get a morphism like this, with some payload. And then I want to compose it with, but you see, M121 is an element which corresponds to, is an element of the form 1, 2 goes to 1. It doesn't match. Okay? But really, whenever I'm trying to multiply two things, implicitly I'm telling to myself, let's apply the identity to the rest. Okay? So really, I want to think of this, so I want to map it into an element of the form E 1, 2, 3, 4, 5, 6 into 1, 3, 4, 5, 6 by extending it by the identity. So I could have made the notation for M more complicated. I could have said, instead of calling it M12 into 1, I'd call it M12 into 1 with further variables 3, 4, 5, 6 on which we act by the identity. But it's cumbersome. So instead, I kind of extended the category. So I declare that if you want to compose two morphisms, so if you want to compose an E from A to B into A1 to B1 with an E A2 into B2, if B1 is not equal to B2, you just add identity elements here as many as you need, and identity elements here as many as you need for the extra elements. So this is the definition here. First of all, I define set difference. So A minus B is defined to be the complement inside A of B. That's nothing. And then, if you want to multiply an E from A1 to B1 with an E from A2 to B2, and B1 dual is not A2, if it is A2, we've already defined it. If it's not A2, then I take the first E and extend it by the identity. What does it mean to extend it by the identity? It means you take A1 and you add to it everything in A2 which is not in B1. So basically, think like that. So I'm trying to compose A1, B1 with A2, B2, but B1 and A2 are not equal. So B1 and A2 intersect to some extent, but also have extras. So what I do is I extend, I should have written it here. I extend the first morphism, omega 1 e to the q1. I extend it by the identity with strands corresponding to A2 minus B1. And then its new domain will be A1 union A2 minus B1. A2 minus B1. And likewise, I extend this one with elements corresponding to also to A2 minus, to B1 minus A2. So now the output will be B2 union B1 minus A2. So these are the identities that I've added. So this is what's written here. So I extend the first by making its domain larger and adding an identity. An identity is just the sum of a letter times its dual, where the summation is over the relevant summation, A2 minus B1. So A2 minus B1. Likewise, I extend the second morphism by adding an identity, and then I compose like in the old times. So that just makes things simpler. So, done. Now, now I finally enter R and C. So R is, so I had to fix for rotation numbers. But anyway, R is t to the 1/2 times 1 minus t pj xj plus t minus 1 pi minus xj. I think it's the same formula that I wrote before, but slightly or reorganized. Okay? And likewise R bar, and likewise C and C bar, and likewise eta. And the most interesting thing is the multiplication tensor. So multiplying I and j into k is a morphism from pi I psi I, pi j psi j into pk xk. And this is the formula we wrote at some point. So this is the term that comes from the Heisenberg algebra. This corresponds to multiplication in the polynomial ring, and this is the extra term coming from the Heisenberg algebra. So I execute this, execute this, and now everything is just stupid. I want to compute or check Reidemeister 3. It's actually the same check as before, because all the symbols, I mean, it's the exact same formulas as before. I could have done it step by step. So I could have first printed this, and that's a product of E-morphism, so it's a big E-morphism. I could have, then I can compose it with the first multiplication, I get something, well, things get simplified a bit. Basically, it's the same thing that we've done before, so I have nothing to say. Likewise for Reidemeister 2, the 2 versions of Reidemeister 2, and finally the 4 versions of Reidemeister 1, everything works. So now if I want to compute the invariant of a tangle, say this tangle, all I have to do is to enter, so it's a crossing 1/6, and then another crossing 7/4, and another crossing 5/2, 1/6, 7/4, 5/2. I hope the signs are right. There is also one place where the tangent is pointing to the right. This is here, so that's the C bar 3, and then I just multiply. Here it is. That's the value of this tangle. That's the invariant of that tangle. Good or bad, this is it. Yeah?
Isn't it like the strand on the left was 1, 3, 4, 5, 6? So shouldn't it be 7/3?
Sorry?
Shouldn't it be 7/3 instead of 7/4?
No. Sorry, the thing I'm labeling here is not the edges, but, okay, so really you should read this as follows. Yes, sorry, I need to copy the tangle, so. Okay, this is the tangle. I want to write it as a product of generators and then multiply. So to write it as a product of generators, I need to cut. So I cut here, I cut here, I cut here, and I cut here, and I cut here. And now, now I have 3 tangles in the picture, right? A crossing, 4 tangles in the picture. A crossing, another crossing, another crossing, and a rotation element. Okay? So I need to take the product, the tensor product of all of those. So I need to choose names for the tensor factors in which this will live, the tensor factors in this will live, and so on. So my choice of names is written there, except I didn't write the cuts. So the tensor factors are named 1, 3, 4, 5, 6, and 2, and 7. Okay? So 1 is the tensor factor running from here to here. 3 is the tensor factor running from, from here to here, and so on. And then this is a crossing in which factor 1 goes over factor 6. This is a cap for factor 3. This is a tensor, this is 7 goes over 4, and so on.
Okay.
And then I actually need to multiply along this strand. So I need to multiply tensor factor 1 with 3, with 4, with 5, with 6. So 1 with 3 and put the output in 1. 1 with 4, put the output in 1. 1 with 5, put the output in 1, and so on. So, okay? Anyway, that's the invariant of that temple. You could call it uninteresting. I mean, it's fine. We're somewhere in the middle. Now I could compute the invariant of the knot 4-1. And if people are familiar with sort of knot will sort of see that this looks like 1 over the Alexander polynomial. So in fact, let's compute the Alexander polynomial of the knot 4-1 and using the built-in program, and it's the same. I mean, it's the same up to, it's 1 over. Okay? So let's check if this is general. So for all nodes with up to 9 crossings, let me compute the Alexander polynomial and multiply it by our invariant, but taking only the first component. So ignoring the quadratic, taking only the omega part. So take our invariant and take the first part. So let's do it for all nodes with up to 9 crossings. And this takes actually a little bit of time. So before we suppose, sorry, so I'm multiplying the, I'm computing the product, so I should be getting a list of ones. 1, 1, 1, 1, 1, 1, 1, right? But anyway, before we check if this is what comes out, before we see if this is what comes out, comes the question. So, oops, it's not what came out, but let's talk about it later. The question is, well, can you prove now? It seems that we have a conjecture. Can we prove that this crazy infinite dimensional technique we just cooked gives the same answer as the 4-dimensional algebra we were talking about a couple of weeks ago? I mean, there is a hidden conjecture here. So, again, my tendency is to say, oh, I know it's true. Now it's a matter of technical work. Now it's a matter of, once you know that something is true, proving it is kind of a minor, is much easier. So I actually know how to prove it, but to tell you the truth, to be honest, my proof is extremely indirect. So if you could come up with a simple proof, that would be delightful. Anyway, what are those signs? So I actually was puzzled a little bit by these signs myself. It took me time to understand what they are. And first of all, we're seeing that up to a plus or minus factor, these polynomials agree. So I mean, there is something there for sure, okay? But still, y plus minus 1. And I think this has to do with, so it has nothing to do with mathematics and has to do with Mathematica. So I think like the programs end up computing the square root of a determinant. And Mathematica at some point makes an arbitrary choice. And so we get basically random sign errors. And I think that's all that is. I don't think there is any content to it. So, let me remind you, sorry, I'll go a few seconds over time, but, let me remind you that 1 is equal to the square root of 1 times 1, which is equal to the square root of minus 1 times minus 1, which is equal to the square root of minus 1 times the square root of minus 1, which is equal to I times I, which is equal to I squared, which is equal to negative 1. So I think that's what's happening here. So that's all. And then the last thing is let's compute the Alexander polynomial of GST 48. And So this is a bit random. Anyway, it took 10 seconds, which is better than what we had before. The programs are awful. Had I written them well, it would have been much faster, because this is actually a polynomial time algorithm. Because maybe it's complicated, but the space of quadratics is actually tiny relative to some two-dimensional space raised to a high power. Okay, let's quit and yeah, sorry. So let's not quit yet. Yes, Jesse.
Sorry. Another question about the diagram.
Yeah.
Are the C's? Are we treating them as caps or as full C's in this example?
I am counting. So. So, strictly speaking, this is an illegal crossing because it is not the case that both arrows are pointing up. So really, I would have to rotate. So really, to write it in this sort of standard form, I would have to rotate it 90 degrees.
We could put like a C bar between 4 and 5 instead of a C bar.
If I rotate it 90 degrees, this should look like this. Oh, you're right. So no rotation number. Wait, what do I want to say? So I suppose I'm counting rotations when I wait, if I rotate it. I mean, there is a rotation here, but I'm a bit sorry.
Slide the right-hand strand over top of the cap leftwards.
Yeah.
And we can have the rotation number occur on the far right-hand side. And then it would be a full C bar.
So, yeah, I'm sorry, something confuses me, and maybe it's not the right time. So I owe you an answer. Okay? Sorry. Okay. Okay, so see you on Monday.